When you hear software engineering, your mind probably jumps to sleek mobile apps, complex web platforms, or massive AI models running in the cloud. But look around you. Billions of tiny, hidden computers are woven into the objects in this room, buried inside everyday devices, and waiting for a command to trigger a physical response. We call these embedded systems. Instead of a general-purpose computer that handles everything from gaming to spreadsheets, an embedded system is a microprocessor designed to do one specific physical task flawlessly. While they might just spin the drum of a washing machine, they also bear immense responsibility. Commercial aviation, for instance, relies entirely on these single-purpose processors to keep hundreds of tons of metal safely in the air. Consider the flaps on an airplane wing. When a commercial jet comes in for a landing, these heavy panels extend downward to dramatically increase drag and reduce airspeed, allowing the plane to land safely on shorter runways. Which brings us to the core challenge of embedded engineering. How exactly does a digital line of code safely and predictably command that kind of extreme physical force? Building a system that can move a wing flap starts with a systems engineer. They have to calculate the exact computing power, memory, and energy requirements needed for the job, and then select the appropriate microprocessor architecture. This map of the system is a block diagram. It outlines how the central processor will physically connect to the external sensors and the high-power motor drivers. Alongside this, they generate a strict bill of materials, detailing every physical component required. Once that blueprint is locked, the development process immediately splits into two distinct tracks running at the exact same time: hardware and software. Translating digital intent into physical motion requires bridging two entirely different worlds. You have to construct the physical electrical circuits to handle raw power, and you have to write the digital logic to control it. A common misconception is that embedded hardware engineers physically manufacture the microchips themselves. They don't. That precise silicon fabrication is handled entirely by VLSI engineers. The embedded hardware engineer takes that pre-existing chip and designs the printed circuit board, or PCB. They are building the physical nervous system around the digital brain so it can communicate with the outside world. Out in the real world, and especially high in the atmosphere, these delicate electronics are bombarded by intense electromagnetic radiation. The hardware team must meticulously design the board's traces and shielding, ensuring outside interference doesn't corrupt sensors reading the flap's position. There is also a major physical constraint. A microchip operates on tiny fractions of an amp. It cannot output nearly enough raw electrical current to physically force a mechanical wing flap to move. This chart shows a PID controller feedback loop in action. Because the hardware team has to use heavy external drivers to amplify the chip's current, they must carefully tune this control loop. This ensures when the motor forces the flap to 30 degrees, it slows down and locks into place without overshooting the target. That is the hardware engineer's true value. They create a stable, protected environment that translates incredibly weak digital signals into precise, massive physical force. While the hardware is being designed, the software engineer is coding the logic for that exact processor. And here we hit one of the most stubborn myths in the industry regarding the language they write in. You will frequently hear people claim that embedded systems are written in a special, distinct language called embedded C. In reality, no such language exists. It is just standard C programming. The difference lies entirely in memory control. When writing software for a laptop, the compiler decides where to store variables. But in embedded systems, engineers use linker scripts to force variables into exact, non-negotiable physical hardware addresses on the chip. Writing embedded software is an uncompromising discipline. You aren't just creating logical loops, you are dictating the exact physical footprint of your code down to the final byte. Before that C code can even run, the system needs to wake up. That is the job of the bootloader. The very first piece of code executed the millisecond power hits the chip. The bootloader serves a critical safety function. It initializes the hardware and mechanically forces the wing flap to a safe, default 0-degree position. Only after the system is stabilized does the main C firmware load into memory, immediately firing rapid, precise digital commands through communication protocols like UART or SPI directly to the heavy motor driver. This is the moment the parallel tracks converge. The software logic finally meets the physical hardware, and test engineers begin running grueling hit-and-trial stress tests across hundreds of different scenarios. They rigorously evaluate the skew sensors. If the left wing flap lowers to 15 degrees, the right wing flap must mirror it perfectly in real time. If it doesn't, the aircraft will experience a catastrophic aerodynamic imbalance. A fully realized embedded system leaves no room for error. Its survival depends entirely on digital intent commanding physical reality under extreme, unforgiving stress. This uncompromising environment demands a rare breed of engineer. You have to be a fluent software coder who is completely comfortable reading complex 100-page electronic hardware datasheets. Engineers with this hybrid skill set primarily flow into two massive industries. Many go into consumer electronics, writing the logic that powers modern home appliances and smart devices. Others enter the semiconductor industry directly. Here they write the base firmware for the chip manufacturers themselves, a highly technical role that commands premium salaries on par with the engineers who design the silicon. This architecture scales from the smartwatch on your wrist to the commercial jet crossing the Atlantic. Regardless of the task, these systems all rely on the same fundamental principles of hardware-software integration. Cloud servers and web platforms get the public glory, but our daily physical reality functions because of these specialized systems and the hybrid engineers who bridge the gap between code and hardware.